also cylindrical capacitor. This is also not in our syllabus. And there are changes in the syllabus, like here you can see here energy is stored in capacitor. Actually, I am this will be our next topic, and we don't require the derivation. Okay, we will only write the formulas and solve the question. So I think this is a positive point for you. So this or nothing else is changed in the syllabus. The first chapter, all things are included, and this is the change, and accordingly I will tell you according to the chapter. In the current electricity there are some changes in the current electricity chapter. Next chapter after this there are some changes, I think so. So we have completed Hamza, till where we have completed. Do you have any idea?
Sir, actually, I'm outside in the sand dunes. I don't really have my book here. I need
No
to,
problem.
yeah.
Okay. No problem. So means I have completed. We have an idea now. We have completed this, and this also dielectric fully filled between plates, and dielectric partially filled between plates. Okay. So I think um, what batch is MEG. This is MEF. In MEF, I have completed this today. So MEG. Okay. So Hamza, uh, so now should I start? Are you
Yes,
okay?
sir. Yes, sir.
Are you comfortable? Okay, that's fine. So I am believing that we have completed till here. So Hamza, let's recap. I am recapping. We have the capacitor. What are capacitors? Please listen carefully. Capacitors are nothing but they are two oppositely charged conductors separated by some medium. Medium can be air, medium can be oil, medium can be dielectric. Okay. After that, there are three types of capacitors. I have told you that there is one parallel plate capacitor, spherical capacitor, and cylindrical capacitor. And two types of capacitor like spherical and cylindrical are not in our syllabus, so we will not study this. And after that, we have discussed the parallel plate capacitor. What are the parallel plate capacitors? Parallel plate capacitors are simply two parallel plates. The plates can be rectangular or can be in circular form. Okay. And after that, I have told you parallel to calculate the capacitance when air is placed in between the plates. And after that, we have calculated when dielectric is fully filled between the plates. After that, we have completed the dielectric partially filled between the plates. And now, I think uh, we should start from parallel plate capacitor. Do you have copy or pen, anything? Hamza,
Yes, sir.
do you have pen or copy with you?
No, I can
Okay,
take
no problem.
screenshots.
Okay, fine, no problem. You are not at your home.
Yeah, I'm at the sand dunes.
Okay. So please try to understand. Understanding is important, not copy or pen.
Okay.
So parallel plate capacitor with conducting slab partially filled in between the plates. Let's see, Hamza. This is the front view. You can see here, like these are the parallel plates. And now you are only seeing this part. This is the straight line you are only seeing. So you are only seeing the front view of the plate. So we make capacitors, we represent capacitor like this. So already told you, one plate have positive charge and another plate have equal amount of negative charge. Very simple topic. And I have told you that first we will calculate the electric field. First we will calculate the electric field. Can I rotate this? How should I rotate this? Rotate at 90 left. No. Rotate at 90 left. Rotate at, now it's okay. Now it's okay. Now I am placing this. What happened? So Hamza, these are the plates. Here you can see this is a negatively charged plate. Now I am placing the plates like this, like this. So you can see this is one plate, this is one plate, this is another plate, like this. So what you will see, my line, my straight hands line. You will see two straight lines. Like here is one plate and here is one plate, and this plate is like this in actual. This plate is like this in actual, and this have a positive charge, and this plate have a negative charge. This plate have a negative charge. And these both the plates are separated by distance d. And now what I am doing, I am placing a not dielectric, a conducting slab. Oh, Hamza. Hello, Hamza. What happened? Hamza, am I audible?
Answer.
Hamza, am I audible?
Yes, sir.
You can message. Okay, you can message me. No problem. So this distance is d, and the thickness of this conducting slab. This is conducting slab. This is conducting slab. Conducting slab, or you can say this is a conductor. And we know that inside the conductor, suppose this is a point P. This is a point P. And I want to calculate electric field at point P, means electric field at point P will be 0. Point P will inside the conducting slab. Here the electric field is 0, EP. E suffix P means electric field at point P is 0. Electric field is 0 at point P. So at point P is 0 means electric field inside the electric field inside whole of the conductor is 0. So you can write here electric field inside the conductor is 0. We have discussed this thing many times. We are taking the conductor, like I have told you, I have a conductor like this, and suppose if I am giving a charge to the conductor, this charge will always appear on the surface. So there is no charge inside. This is the property of the conductor. There is no charge inside. So inside the electric field will be 0. Everywhere inside the electric field is 0. Okay. And this thickness is T. So means in thickness T, the electric field is 0. I can write here in thickness T, electric field is 0. But we have one more thickness, this thickness. This is a space. But in this space, what is air? Air is in this space. So in air, We know at each and every point the value of electric field in air is, do you remember, Hamza? ELD, electric field in air between plates. I am representing it with E naught, and this E naught is given by sigma y epsilon naught. And one thing more, this field, what is the thickness of this field? Means what is the region in which this field is present? Hamza?
Yes, sir.
Can you tell me the thickness? I am saying that I meant to say that tell me the region of electric field of air, like in a region D minus T, na? In a region D, in you can see from here, in T region, for the T thickness there is no electric field, but for D minus T thickness there is air, but in air there is electric field. So this electric field, this E naught, present in D minus T thickness. Now this is sigma. Sigma is known as surface charge density. And sigma is given by charge divided by area. Charge divided by area. Now, if I want to calculate the potential, I am having a formula, electric field into separation of electric field, means I can say region separation. Simply you can say separation. What separation? Separation in which the electric field exists. Separation in which electric field exists. Earlier, what we have doing, in whole of the region D, the electric field exists E naught. That's why I have written the formula V is equal to E naught into D. Now I will write the formula E naught into separation of E naught, D minus T, and E conducting into T. This is E conducting. EP, I am representing this E conducting, electric field in the conductor. You can write here EC is electric field in region T thickness. Region of T thickness. Region of T thickness. So total potential E naught is sigma by epsilon naught, and this is D minus T, and EC is 0. Electric field inside the conductor is 0, and this whole term will become 0. So we have V is equal to sigma y epsilon naught into D minus T, and we have sigma Q by A and this is d minus t. So we have potential now. So can I calculate capacitance? Capacitance is Q by V. Now put the value of d minus t, and you, after that you will get epsilon naught A divided by d minus t. This is the capacitance, resulting capacitance when conducting slab partially filled. Please take the screenshots. Hamza, please take the screenshot. Done? Please tell me, Hamza. Are you taking screenshots? Actually, you can write me on chat box. Hamza, am I audible? Am I audible, Hamza? What happened? Hamza,
Yes, sir.
am audible. Should I continue?
Yes, sir.
You can write in the chat box. Yeah, you can write in chat box. Okay. So okay, take the screenshots. Okay, till here. Okay, and now I am moving forward, and you can write me in the chat box if you have any doubt or anything. You can write the chat box. So there is a question: a parallel plate capacitor with air between the plates has a capacitance of 8 picofarad, and 1 picofarad equal to 10 to the power minus 12 farad. Okay. What will be the capacitance if distance between plates is reduced by half? Is reduced by half, and the space between them is filled with dielectric of constant 6. Okay. So this is the question. And now here is a parallel plate capacitor like this. What is capacitor? This is capacitor, and the distance between them, initially suppose let's say d, and the capacitance when the air is present is given by 8 picofarad, and I can convert this into farad. Okay, and what is the formula of C naught? Epsilon naught A by D. Epsilon naught A by D. This is given by 8 into 10 to the power minus 12 farad. This is our equation number 1. Hamza, these questions are important questions, and these questions can be asked in your examination also. And after that, what we have done, this is the initial condition. And this is final condition. Final condition. Finally, what is happening? The plates of capacitors are same. The area of the plates of capacitor is same, but the distance is reduced by half. But the distance is reduced by half. This is negative charge. And this time the distance becomes d by 2. And area of the plate here is A. And here also the area of each plate remains same. And now what we have done, we have introduced a dielectric here. We have filled this capacitor with some dielectric whose constant is given as 6. Dielectric have a constant 6. So we have a formula for calculating the distance d. Now d will become dy 2. So this will become 2k epsilon naught a by d. And look, Hamza, we have epsilon naught a by d. What is epsilon naught a by d? This. So I can put 2 and value of k is 6. Epsilon naught a by d is 8 into 10 to the power minus 12. So the answer will be 96 into 10 to the power minus 12 farad. So finally we have got 96 into 10 to the power minus 12 farad. This is our final answer. This is our final answer. So Hamza, please take the screenshots of this. This is very important question. Okay, are you taking the screenshots? Okay, fine. Okay, take the screenshot of this and take the screenshot of this. Simply you have to apply the formulas. And there is another question. A parallel, we have the questions of only parallel plates capacitor, not spherical or not cylindrical, because those are not in our syllabus. So there is a question again. In in a parallel plate capacitor with air between plates, each plate has an area six into 10 to the power minus 3. 6 into 10 to the power minus 3. Meter square. Meter square is the unit of area, and the distance between distance between the plates is 3 mm. Calculate capacitance of capacitor if this capacitor is connected. This capacitor is connected. Hamza, now am I audible? Okay, so actually I thought that your internet connection is not working properly. So listen that this is the question. Okay, please read this question. Calculate capacitance of capacitor if this capacitor is connected to a 100-volt supply. 100-volt supply means you are connecting this capacitor with battery or cell or with some power source. 100-volt supply. Okay. What is the charge on each plate of capacitor? Each plate of capacitor. If you have any problem, you can write in the chat box. So this is the question, and now what is happening? What is happening? Here is a parallel plate capacitor like this. Positive charge, positive charge, positive charge, negative charge, negative charge, negative charge, negative charge. And separation is 3 mm, means D is equal to 3 mm. First convert the mm into meter. 10 to the power minus 3 meter. And area is given of each plate 6 into 10 to the power minus 3 meter square. And what will be the capacitance? The air is here. C naught is equal to epsilon naught A by D. Value of epsilon naught is 8.85 10 to the power minus 12 into value of area is given as this and divided by 3 into 10 to the power 3. When you calculate this, you will get the answer 17.70 into 10 to the power minus 12 farad. Now, this capacitor is connected to a battery of 100 volt, and this is positive charge plate, this is negative charge plate. Now we have to find the charge on each plate. Charge on each plate. Charge on each plate, that is Q, and this is equal to Q equal to CV. Okay, Hamza, now it's okay now. Fine. So charge is Q is equal to CV, like we have written Q by V na. So from here I can write Q is equal to CV. And what is the value of CV? C naught into V. And what is C naught? C naught is 17.70 into 10 to the power minus 12. And what is potential? Potential is given as 100 volt. So this will become 17.70 into 10 to the power minus 10 coulomb. Q is equal to 17.70 into 10 to the power minus 10 coulomb. This is our final answer. I have already told you charge on each plate of capacitor will be same. Okay, Hamza? So this is our so Hamza, you can take the screenshot of this question and answer.
Yes, sir.
These kinds of questions you can get in your board examinations. Very easy question. Now there is another very important question. Very important question. Please see this carefully. In the above or previous question, in the above question, explain what would happen what would happen if in the given capacitor a 3 mm mica sheet and dielectric constant is given as 6 is inserted between plates, between the plates. Number A is while the voltage supply remain connected, while the voltage supply remains connected. And another question is after the supply was disconnected, was disconnected. Okay. So Hamza, this is very good question, and earlier we have this. I have made the okay. what we have these and air in between them, and distance is 3 mm. Initially, this is the initial condition. Okay. And area is same, no problem. And we have value of C naught, that is epsilon naught A by D. What was the answer of C naught? Yeah, 17.70 into 10 to the power minus 12 farad. In the above question, we have calculated this. And they are asking what is the A. What happens when voltage supply remains connected? A part. Like here voltage is 100 volt and this remains connected. And this is positively charged plate and this is negatively charged plate. And in between the plates, mica is filled fully filled. Mica is fully filled. You can see. And here K is equal to 6 of mica. And if K is equal to 6 of mica, then number 1, capacitance will become K times of C naught. We have discussed this. K is 6 and C naught is 17.70 into 10 to the power minus 12. So this will become the value of C naught. Okay. This is the value of capacitance. And this will be in farad. Now, if battery, if supply remains connected, means voltage will not change. Will not change. Voltage will not change means you are supplying the energy again and again. Voltage is energy. You are supplying the energy again and again means charge will change. Charge will change, no? So,
Yes.
so we will see how the charge will change. Here you can write, but charge will change. This is one of the important questions. But charge will change. Why charge is change? Because we have a battery and battery is giving charge. So charge will change. So what happens? Potential will remain same. Vm means potential when mica is introduced. That will be same as before. We don't write this. Okay, fine. And that is 100 volt. Earlier, we have a charge Q naught. Here is a charge. I am representing charge initially Q naught. This is plus Q naught, and here is minus Q naught. Earlier charge Q naught is given by C naught and P. Okay. Earlier charge is this, and now after introducing the mica, and remember the supply is connected, then charge when mica is connected will be charge is capacitance into voltage into Vm. Okay. So capacitance, what is the capacitance? K times of C naught, and Vm will remain same. Vm is equal to V. So value of K is 6 and value of C naught is 17.70. So you can write 6 C naught V. C naught 6 into value of V is 100 and this is C naught. So you can write Qm will become 600 and C naught is 17.70 into 10 to the power minus 12 farad. So now the charge is this, means charge will increase. See here, if the battery remains connected, the charge will increase. Okay, so we have seen that there are two quantities here. One is potential, one is charge. So when the battery remains connected and a dielectric of mica is introduced in between the plate, then the potential, or you can say potential difference, will remain same, but charge will change, means charge will increase. Now there is another case in which the battery disconnected. Another case, now battery, or you can just supply disconnected. Now you can imagine if you remove the battery from the capacitor, what will happen? What will happen? Means the charge will remain same, means no charge is coming from the external source. Hamza, have you understood now? Means no charge you are giving this time, means the charge given earlier will remain same, but it will not increase. So battery remains connected. You can say charge will remain same. And what about the capacitance? What about the capacitance? Capacitance is K epsilon naught A by D. K is changing, not changing. Epsilon naught is not changing. A is not changing. D is not changing. Means capacitance will not change. If capacitance is not changed and charge is changing, capacitance is not change and charge will remain same. and you can calculate the potential. What would happen with potential? V is equal to Q is equal to CV, V is equal to QM divided by CM. So now see, Hamza, hmm, charge is not changing. Charge is not changing, and capacitance also not changing. Means the potential is not changing, but this is not correct. Hmm, give me a minute. Hello, Hamza. Hello. So,
Sir, some internet problem is there here.
what?
Sir, some internet problem is there. That's why I'm getting disconnected.
Okay, no problem. No problem. So, so here you can see that. Here you can see that. First is while the voltage supply remains connected. Voltage supply remains connected means voltage will not change, but charge will change. So here voltage remains same and voltage remain, charge will change. And here what happened? Here what happened? After that we have connected the, uh, we have disconnected the battery. So charge will change. Okay. So charge will change. Here you can see. Sorry, when battery is disconnected means charge will remain same. Charge will remain same, and potential is, charge is remain same, and capacitance, actually capacitance is changing. Why? Capacitance is changing because we are introducing a dielectric here. Okay, we are introducing a dielectric here, so capacitance will increase. Okay, this whole thing will multiplied by k, and k is greater, k is 6, so means capacitance will, Cm will increase. If Cm will increase, then charge is same, then what would happen? Potential will decrease. Okay, so you can say potential decreases. Okay, Hamza, please take the screenshot. I am continuously taking classes
Yes,
from
sir,
last,
I took screenshot.
what?
Sir, I took
Taking the
screenshot. Yes.
screenshot. This one.
1 minute.
Okay, done na? This one also.
Yes.
And this. Okay, Hamza. So actually, we have 2 more minutes. I am taking classes since the last 6.5 hours continuously. Okay, and now we have done with this. So please revise your notes and try to remember the concepts, the formulas, important formulas, and revise the questions. And please try to be sincere. Okay, Hamza?
Yes, sir.
Okay, Hamza, we have 1 more minute, and after 1 minute, you can leave the meeting. That's all for today. And in the next class, we will discuss about the uh, energy stored in capacitor. Okay, okay, Hamza, that's fine. Now you can leave the meeting. And thank you for joining.